Hi everyone. In this video, I'm going to talk about simulations. This is a supplemental topic, which means that it's not in your textbook. Really quick, think of a whole number between 1 and 4. I'm going to come back to this in a second. I want to start by talking about randomness. I've read that our brains have a really hard time with noticing random events. Something with the idea that we desire to see patterns so that we can make predictions and feel safer. So the idea of things being random freaks us out. But actually, a lot of random events are very ordinary. We don't notice them. But every once in a while, there'll be a random event that's extraordinary, and that's what we notice. So we've kind of misused the term to then talk about extraordinary things, right? You hear somebody say, oh, wow, that was so random. But what they really mean is, that was really unexpected or that was really extraordinary. It wasn't actually a random event. And the other times that I've heard people use the word random inaccurately is when they're trying to describe doing something without a lot of thought. Like I randomly picked a sandwich off of a menu. But you can't actually do something without thought. We all have bias. So, for example, most of you probably picked the number 3. Unless you've heard of this, and then you maybe picked the number 1 because you know that most people are going to pick the number 3. But the most popular numbers that are chosen when you ask people to choose between 1 and 4 is 2 and 3. And 3, it's like 75% of people will pick the number 3. So we ourselves, we cannot actually do anything randomly. We can't act randomly. But random is actually a really important concept in statistics. And so we need to actually be able to create random events. So how do we actually generate a random event? Well, one way that we can do it is rolling a die. What makes rolling a die random? So let's talk about what randomness is instead of what it isn't. So an event is random if all possible outcomes have an equal likelihood of being selected. So again, think of rolling that die. Number 1 is as equally likely to show up as number 5 or 6 or 4 or 3 or 2, right? Each one has an equal likelihood of showing up. The second thing, an individual occurrence cannot be predicted, right? If I roll the die and get a 5, and I go to roll the die again, I can't predict what I'm going to get next. I can guess, but I can't predict. And it doesn't matter that I rolled a 5. Whatever I rolled before has no bearing on what I'm going to do next when I roll a die. And then finally, if I do this act of rolling a die a large number of times, I'm going to get a uniform distribution. So if I roll this die 10,000 times, I'm going to see the number 1 the same number of times that I see the number 2, 3, 4, 5, and 6, giving me this uniform distribution. There are a few other ways that we can generate random outcomes. We can flip a coin. We could pick a card out of a deck of cards as long as we've shuffled that deck a whole bunch of times. Another one is to pick a name out of a hat. Probably the best way is to use a computer. There's a good website at random.org where you can generate random numbers. Our calculator will generate pseudo-random numbers, meaning they've used an algorithm to create random numbers and therefore they're not actually random. But they're close, and for the purposes of this class, they're close enough. So again, the topic of this supplemental topic, that sounds weird, is simulations. So what is a simulation? A simulation mimics reality by using randomness to represent the outcomes of real events. Ever since the pandemic hit last year, I've actually heard a lot about simulations in the news, especially in the beginning. I thought one of the interesting simulations that showed up was in this article in the Washington Post, where they were using simulations to try to give people a visual effect of how the virus will spread depending on different situations. So I've got the link here if you're interested, but I just want to give you a real world example. So when do we use simulations? Why do we use simulations? Right? They used simulations a lot during the pandemic because it was this brand new virus. They really didn't know what was going to happen, and they were trying to make predictions. We also use simulations when something's, just too expensive to actually do in the real world, or it's too unrealistic, or maybe it's unethical, right? Maybe it involves, trying to understand children, but we don't actually want to, do an experiment on children. So we run a simulation instead. Simulations are another kind of model. So we've talked about the normal model, we've talked about linear regression models, and now we have simulations, which are another form of a model. So I want to talk about how we are going to use simulations in this class, and we're not going to do anything as complicated as what I had on that previous page. Ours are going to be pretty straightforward, just to give us some practice with just kind of setting up a simulation, understanding what they are, but really getting down to what is randomness and what does it mean and how do we use it. And this is pretty important when we get into Unit 3. So I'm going to talk about the 4 steps of designing a simulation using an example. So here we have an example where we're going to flip 2 coins simultaneously, 1 quarter and 1 nickel. And this says, what are the chances that we're going to get 2 heads? And we're going to use a simulation to answer this. Now, I know that we can calculate this with a theoretical probability, but that's not the point. The point is that I wanted to give an example that you could really visualize. In fact, we could actually get out a quarter and a nickel and flip them 20 times and see what happens. But instead, I'm trying to use this as a way to describe how we will set up simulations. So the first step when we're thinking about simulations is to describe how we're going to assign random numbers to the possible outcomes for a component. Now, the component in this case is flipping a coin. So what we are going to do is we're going to generate numbers, whole numbers, between 1 and 2, and we're going to let 1 represent flipping a head and 2 represent flipping a tail. The next step is going to be that we want to describe how we're going to create a trial. So a trial in this case would be flipping the 2 coins. So what we're going to do is we're going to generate 2 numbers for each trial. The first number will represent the nickel, and the second number, or what do I have? The first number will represent the quarter, and the second will represent the nickel. If the outcome of the trial is that I get 2 1s, I'm going to record yes for the outcome, meaning yes, I got 2 heads. If I get anything else, if I get 2 2s or a 1 and a 2 or a 2 and a 1, I'm going to record no. This is going to make more sense on the next page. So now I'm going to take that setup and I'm going to run 20 trials. So I'm going to show you how to generate the pseudo-random numbers in your calculator and fill out this table. So notice I have 20 trials here. For each trial, again, I'm going to generate 2 numbers between 1 and 2. To do this with a calculator, we're going to use the randint command. This means random integer. We'll always use whole numbers actually, but we're still going to use the randint command. The first number that you put in for this command will be the lower bound of the range of numbers that you want, then the upper bound, and then the total number of numbers. So in this case, I want numbers between 1 and 2, and I want 2 of those numbers. To do this, we're going to go to this math button right here. So let me play this video so that you can see this happen. So I'm going to go to math and then arrow over to probability. And you can see in mine, randint is number 5. I get these prompts. So I'm going from 1 to 2, and I want 2 numbers. And then I'm going to paste. And then hit enter. Now I want you to notice as well that I can just hit enter a whole bunch more times. Once you, oops, it started over. I hate that. Okay, once you put in the randint command, you don't have to do it 20 times. So again, I'm just going to fast forward. So right here, I hit enter to get that 1, 1. And then all I did was hit enter again, and it immediately pasted and gave me another 1, 1. And then I just hit enter again, and it gave me a 2, 1, and then again, it gave me a 2, 2. Now, if you've never used this command before, and you go and use this command right now in the exact same way that I am, you'll probably get these exact same numbers, which is just more proof that these are pseudo-random. I also didn't use this calculator to fill in my table because you can see that in trial 1, I don't have 1, 1 here. I had this table filled out before I made the video. So basically, I hit randint 20 times. I just hit enter 20 times, and I got all the components. Remember that we're looking for 2 heads, so I'm looking for trials where I got 2 1s. When I got 2 1s, like I did here, then I recorded a yes. And you can see that of the 20 trials, I got yes 5 times. And so the last step in our simulation is to state our conclusion. And this says, according to my simulation, the chance of getting 2 heads is 5 out of 20, which is 25%. I want to make a note here. Notice that I said according to my simulation. My simulation gave me 25%, which actually, if you calculated the theoretical probability for this, you get the same thing. But if I did this simulation again in exactly the same way, I could have gotten 20% or 35% or 30%. I'm not always going to get 25%. And if we were in a classroom, I would put you guys into groups, and I would have, groups of 2 all do this same simulation, and you would see that a whole bunch of you come up with different outcomes, just slightly different percents. This is called sampling variability. It's going to happen when the number of trials that we're running is really small, and 20 is really small. Now, if we were running a simulation with 10,000 trials, then we would get close to 25%. I mean, really close, if not right on the dot, almost every single time. But because we're only running 20 trials, again, you might do this and get 20% or 15% or 30% or 35% or 45%. It's going to kind of hover around the 25%, but we're still going to get that variability. That doesn't mean that anything's wrong. This is where we have such a hard time with randomness, right? We have this natural variability, and it doesn't mean that anything is wrong. So again, I'm always going to say that according to my simulation, this is the chance. But according to somebody else's exact same simulation, just with different outcomes from their components, might have a slightly different answer. So here's another example. In a Monopoly game, if you land in jail, you have to roll doubles to get out of jail. You get 3 chances to roll doubles, and if after 3 chances you don't roll doubles, you have to pay a $50 fine. So what are the chances if you land in jail that you're going to have to pay the fine? We're going to describe how we will set up a simulation and run at least 20 trials. And if I remember right, you can just pay the fine and not try to run doubles, but we're going to forget that piece. Okay, so remember the first 2 steps are really describing our simulation, and you want to make sure that you do this really well. I'm going to talk about the range of the numbers that I'm going to generate, and then how many of those numbers I'm going to generate and what a trial will look like. So in this case, I'm simulating rolling dice. So I'm going to generate numbers between 1 and 6. I want to look at pairs to see if I've gotten a pair of the same number. So for each trial, I'm going to generate up to 3 pairs of numbers. And if I don't observe any of the same pair, same number in a pair, then I'm going to record that I have to pay the fine. But if I generate 2 numbers and they're the same, like in trial number 10 here, I'm not going to keep generating any numbers. I rolled a pair right away, which means that I don't have to pay the fine. So I'm going to say no. And then the question is, according to the simulation, what's the probability that I have to pay the fine? So I use the randint command in my calculator. I'm generating numbers between 1 and 6, and I want 2 numbers at a time. So I did this again with 3 pairs, up to 3 pairs for each of the 20 trials, and recorded the outcome. Just a side note, there are other ways that I could set up this simulation and still have it be correct, right? Some people might say, well, I'm going to generate numbers between 1 and 6, and I'm just going to generate 6 numbers right away. And then I'm going to look at the first 2, look at the 3rd and 4th, and then look at the 5th and 6th. And if I see a pair, then I'm going to say that I don't have to pay the fine. But again, you just have to make sure that you thoroughly explain what you're doing in your simulation. And there are other ways other than just looking at pairs this way, that we can run this simulation. But after that, after we've got our table filled out, then we can get to the conclusion. Don't forget to say according to my simulation. So according to my simulation, there was 11 out of the 20 times where I had to pay the fine, which means for this simulation, there was a 55% chance of paying the fine. Again, you might run the exact same simulation, exactly the same way, and get a slightly different percent here. So some concept questions. If a trial shows doubles, and I'm referring to the last example, so say I roll doubles, what is the next trial less likely to get doubles? So if I roll doubles 4 times in a row, am I less likely to roll doubles on the 5th time? And the answer to that is no. It doesn't matter what I rolled previously. That has no effect on my next roll. And this is what we call independent trials. The first trial has no effect on the next trial. I would say there's a lot of people that have a hard time with that idea. Right? I rolled doubles 4 times in a row. Are you really telling me that I have the exact same probability of rolling doubles again? And the answer is yes. Now, if I asked you to calculate the likelihood that you would roll doubles 5 times in a row, you're right, it's going to be small. But individually, the next roll is not dependent on the first roll. All right, the next question. Will simulations of the same scenario result in the same conclusion? I think I emphasized this enough. No. Your simulation might be a slightly different conclusion than my simulation or somebody else's simulation, even if we set them up exactly the same way. This is why it's important to make sure that you're very clear on how you set it up and that you show your table really well. The last question, are simulations considered observed or predicted? So when we're making this table, we are not observing these values. We are still making predictions. We're using random numbers to make predictions. Simulations are not reality. They are a model. So they only predict. Example 7 here is kind of another concept question. It's just a concept example. So it says, a student has trouble getting to work on time. She figures that she's late 30% of the time, on time another 60% of the time, and early only 10% of the time. Since there are 3 cases, she proposes the following simulation model. Randomly generate one number between 1 and 3, with 1 representing being late, 2 representing being on time, and 3 representing being early. Is this an appropriate model for this situation? The answer to that is no. So unlike our previous examples, we don't have an equal likelihood of being on time versus being late versus being early, right? They each have a different percent, which means I can't just have 3 numbers with each one being the same percent of the whole. I hope that's making sense. What's a better idea is if we generate 10 numbers and we let 3 out of those 10, meaning 30% of the numbers, represent being late, 6 out of the 10 numbers represent being on time, and 10% of the numbers, or one number, represent being early. And we don't want the numbers to overlap. So we would let 1 through 3, say, represent being late, 4 through 9 represent being on time, and 10 represent being early. And then the numbers that we have that are representing the events are accurate with the percentage. Let's use this idea to answer the next example. So in this example, we have a student who's taking a quiz with 6 multiple choice questions. After studying, they estimate that they have a 70% chance of getting any question correct. Describe how you will run this simulation and run at least 20 trials. A common mistake with the quiz questions, meaning questions that involve multiple choice quizzes like this, is that people think they have to identify which letter corresponds to the correct answer. We don't have to do that. We just know that there's a 70% chance of getting a right answer. So if we have 10 numbers that we're using, we just want to make sure that 7 out of those 10, or 70% of those numbers, represent getting a correct answer. In this case, unlike the last one, instead of using 1 through 10, I'm going to use 0 through 9. There's a reason that I'm doing this, and that's because when you're programming a computer, actually, using single versus double digits in the same computer program doesn't work. So if I actually want to, if I'm trying to program this simulation, I want to use either all single digits or all double digits. So what is more likely that I would want to do is either use the numbers from 0 to 9 or from 00 to 99, meaning that I have double digits or single digits. I'm going to stick with single digits because this is a nice even percent of 70%. If this is something weird like 57%, then I would go to those double digit numbers. But there are 10 numbers between 0 and 9. And because this is a 70% chance of getting the question right, then I want to make sure that I let 7 of those numbers represent getting a question right. So I'm going to let 0 through 6 represent getting the question correct. And then I'm going to let the other 3 numbers represent getting the question incorrect. So I'm going to let 7 through 9 represent getting the question incorrect. Again, there's other people that might choose different numbers to represent correct versus incorrect questions on this, but this is how I decided to set it up. So I'm going to, because there's 6 multiple choice questions on each quiz, I'm going to generate 6 numbers for each trial. So looking at trial number 1 here, I've got 6 numbers between 0 and 9. And I'm actually, I feel like it's easier for me to count up the number that are incorrect because I'm just looking at numbers 7 through 9. So if you'll notice, I have a 9, a 7, and another 9, which means I got 3 out of the 6 incorrect. That's a bad example because I got 3 out of 6 correct. I am recording the number that I got correct. I'm going to stick with that. Ignore what I just said. All right, so looking at the second trial here, I've got, out of these 6 numbers, 5 of them are between 0 and 6, right? This one, this one, this one, this one, and this one, which means that my quiz score is 5 out of 6. All right, so we do that for every single trial and record the outcome. How many questions out of 6 did we get right on this quiz? Down below, I've got 2 questions that are slightly different. One that's a lot like what I've already asked with all the other simulation questions. According to this simulation, according to my simulation, what is the chance that this student gets all the questions right on the quiz? Well, there's only one trial where I had a perfect 6 out of 6. So the probability is 1 out of the 20 trials, which is 5%. But another question that I can ask with regards to simulations asks for an average. So I could also say, according to the simulation, how many questions on average will the student get correct on the quiz? Remember that an average is adding them all up and dividing by how many there are. There are still 20 trials, so I'm just dividing by 20. But now I'm going to add up the number of questions that were correct on each quiz and divide that by 20. So get 81 out of 20, which averages to be 4.05 points out of 6. So that's the average for these 20 trials. Again, this is my simulation. I could get slightly different outcomes for different simulations. All right, please let me know if you have any questions on simulations.